If we have a metal plate and if electromagnetic radiation of sufficient frequency falls on the metallic surface, then photoelectrons are emitted. This phenomenon is what we refer to as the photoelectric effect. Now, photoelectric effect is one of the proof that light can behave like a particle. But the explanation used for this phenomena it is quantum mechanics. Now the question is, why did the classical physics fail so badly in explaining photoelectric effect? This is what we are going to discuss in this video. Let us compare between the experimental observations and the classical physics prediction. In photoelectric effect, it was found that within the limit of accuracy, the process is instantaneous. It was of the order of 10 to the power minus 9 seconds. Now, if we try to explain this from classical physics point of view, so the waves will be falling on the metal surface, and classical physics says that the energy is spread out continuously across the wavefront. So when it falls on the metal surface, it will gradually soak up the energy over time, like a sponge absorbing water. And when the electrons have sufficient energy, then only it can come out. And if you do the math, this process will take months to emit the electrons. When we incident different frequencies on a metal, the photo emission takes place only when it is greater than or equal to some threshold frequency, which depends on the type of metal we are considering. But in classical physics, the energy of the light depends on the intensity, not on the frequency. So there was no concept of this threshold frequency. If we keep the frequency constant and increase the intensity of the light, it was found that more number of electrons are emitted and there was no change in the maximum kinetic energy. But from classical physics point of view, if we are increasing the intensity, we expect more energy falling on the metal surface, and that should lead to more photoelectrons as well as increase in the maximum kinetic energy. If we keep the intensity constant and if increase the frequency, it was found that the number of photoelectrons emitted was the same, but there was an increase in the maximum kinetic energy. And from classical physics point of view, if we are increasing the intensity, we expect more number of photoelectrons as well as change in the kinetic energy. So clearly we have a winner, and classical physics fails to explain photoelectric effect. Then Albert Einstein came to rescue this contradiction. He extrapolated the postulate of energy quantization of oscillators in the Planck's formula of blackbody radiation. He said, don't see the light as a wave, see it as a packet of energy known as photons. By the way, the term photon was coined in 1926 by chemist Gilbert Lewis. And each packet will have an energy given by h into f, where h is the Planck constant and f is the frequency. Now let us try to explain this photoelectric effect using this concept. Using the concept of photons, now instead of seeing wavefronts falling on the surface, we will see as packet of energy falling on the metal surface. When the photon falls on the metal surface, now the electrons can directly absorb that packet of energy. If this packet of energy is sufficient enough to knock out the electron from the metal surface, then the electron can come out and it will be the photoelectron. Now from here we can see that the process is fast, so it's an instantaneous emission. For a given metal and a given energy of a photon, we can write this relation. E is equal to the work function and the maximum kinetic energy. work function is the minimum amount of energy required to remove an electron from the surface. By the way, work function is different from ionization energy because ionization energy is related to the removal of electron from an atom. But work function is removal of an electron from the surface. Now, given a metal, we will have a work function, and this work function can be expressed in the form of the Planck constant into some frequency. Now, if the energy of the photon is equal to this work function energy, then it can remove the electron from the surface. Now, corresponding to this E naught, we can have a particular frequency. So here we can see that the concept of threshold frequency comes into the picture. And when the frequency of the photon or the light, if it is greater than or equal to the threshold frequency, then only the electrons can come out of the surface. If you keep the frequency constant, then the energy of the photon will also be constant because energy is equal to h into frequency. Now, if I increase the intensity, increase in intensity means more number of photons. If there are more number of photons, then there will be more number of photoelectrons emitted, provided the energy is greater than the work function. But what about the maximum kinetic energy? So from the previous formula, we can write kinetic energy max is equal to the energy of the photon minus the work function. Now here, since frequency is constant, E is constant, and the work function is also constant for a given metal, so the kinetic energy will not change. So constant kinetic energy and more number of photoelectrons. If the intensity is constant, then the number of photons will be constant. So if the number of photons are constant, then the number of photoelectrons emitted will be constant. But if I increase the frequency, then I'm actually increasing the energy of the photon. So by using the formula given below, E is increasing, but the work function is the same. So there will be an increase in the maximum kinetic energy. So more kinetic energy and constant number of photoelectrons when we increase the frequency. So in summary, the concept of photon, that is light behaving like a particle in the form of packet of energy, can explain the photoelectric effect phenomena. Thank you everyone for watching this video. Take care.